So next we'll look at question 8.3. Steam is expanded in an isentropic turbine, i.e. during the expansion inside the turbine, the entropy remains constant. It enters the turbine at 6 megapascals and 400 degrees Celsius and leaves the turbine at 100 kilopascals. What is the change in specific enthalpy of the water between the turbine inlet and outlet? So this isn't very different from things we've seen before, right? We're trying to find the change in enthalpy across some device. And to do that, to find the change in enthalpy, we're going to try to find the enthalpy at each state, meaning, of course, we need to be able to define each state. So it's steam, so we can use pressure and temperature. So that's good. We've already defined state one by the question, which is 6 megapascals and 400 degrees Celsius. State two, though, the only information we have is 100 kilopascals. But we also know that state two is going to have the same entropy, and that's because the steam is expanded isentropically. And this is the ideal case whenever we have a compressor or a turbine. We always want it ideally to be an isentropic compression or expansion. And in this case it is. So we, again, for state one, already good there. State two, we will be okay once we determine the entropy at state one, because once we know the entropy at state one, we know that it's the same entropy at state two. And once we know the entropy at state two, we have the entropy and the temperature, and it's fully defined, and we can get the enthalpy in both states, find the difference, and that's the solution. So let's do that. Okay, so we're going to use, of course, the water tables to do this. So before, well, here, let's just write state. This should be a 1. What do we have? Pressure 1 equals 6 megapascals. Temperature 1 equals 400 degrees Celsius. And we already know we're going to need to find the entropy. So let's just leave some space for that. State 2, we're being asked to find the change in enthalpy. So state 2, all we know is that we have 100 kilopascals, and that, 2. And S2 equals S1 equals whatever we find for S1. So let's go see what that would look like. So there. So let's go to the steam tables. We're looking for 6 megapascal. Oh, that's the wrong tables. That's compressed liquid. Excuse me. 4, 5, superheated water. 6 megapascals, 400 degrees Celsius. So actually, while we're here, we'll want to get the enthalpy as well. So we see the enthalpy over here. And over here, we have the entropy. So we're going to write down both of those values. Because we're trying to, all of this is to find the change in enthalpy. So I'll do. Okay, H1 equals 3177. 0.2, 0.2, and that's kilojoules per kilogram. And the entropy at that state is 6.5408. Oops, there we go. 6.5408 kilojoules per kilogram Kelvin. All right. And of course, that's going to be up here, 6.5408 kilojoules per kilogram Kelvin, because going from state 1 to 2 is isentropic, so the entropy remains the same. So of course we want to find H2 so that we can find the difference. So what we're going to do is define state based on the pressure and the entropy, which we know, and find what the enthalpy is at that state. So we know normally after a turbine, we're usually a relatively high quality mixture, but still a mixture. So I'm going to start by looking at the mixture tables, not the superheated vapor tables. Let's go here. And we're looking for 100 kilopascals, pressure 100 kilopascals, so 0.1 megapascals. We're somewhere here, probably, if we're a mixture. So before we saw that the entropy at state 2 needs to be about 6.5. Are we within the range of 6.5? Certainly we are. So we can confirm that we are a mixture. The question is, what's the quality of the mixture? So we're going to do exactly what we've done for internal energy and for enthalpy. And we're going to sort of see how far along we are between this guy. Oops, I don't know why I did that. Between this guy and this guy. We're going to see how far along we are between them, and that's our quality. And then we'll use that to find our enthalpy. So 1.3026 and 7.3594. So what we'll do is we're going to find the quality at state 2 by saying 6.5408. So that's our actual entropy at state 2 minus the entropy of a saturated liquid, which is 1.3026. So we're relatively far along. 1.3026 divided by the difference between the enthalpy, the entropy, the saturated liquid phase versus the entropy at the saturated vapor phase. And that's the value we have in the middle here, SFG. So 6.0568. And if I calculate this, I'll get a value of 0.865. 0.865. So this is the quality, and we're going to use this quality to find the enthalpy. So again, we're going to just do what we've done a million times before. We're going to say H2 is going to be equal to HF plus X2 times HFG. We've seen this before many times, but let's just find what HF and HFG are. So I'm seeing for 100, we have HF is this, HFG is that. So 417.46 plus 0.865, which we calculated over here, times HFG, which is 2258.0. 2258.0. So 917.46 plus 0.865 times 2258. And this is giving us enthalpy of 2870.63. Now, we're not done yet because they don't ask us for the enthalpy, they ask us for the change in enthalpy. So if we do H2 minus H1, H1 minus H2, excuse me. H1 minus H2 is 3177.2 minus 2870.63 equals 3177.2 minus 2870.63. And this gives us a change in enthalpy of 306.57. And that's, of course, given in kilojoules per kilogram. So that means that for every kilogram per second of fluid moving through this system, we are producing at the turbine 306.57 kilowatts of work. And that's what turbines do. They produce work from a flow that's introduced into it. So that's how we do this. It's not too different from what we've seen before with things like internal energy and enthalpy, right? We're finding the quality based on the difference between SF, SG, and where we currently are, what our entropy is. And we're using that difference to then evaluate either the enthalpy, in this case, the enthalpy, but maybe the internal energy in other cases, using this sort of equation. And of course, we're finding the difference to see how much work is being done across the turbine.